We are excited to introduce our paper, Sat to City, 3D city generation from a single satellite image with cascaded latent diffusion. Sat to City is a framework that takes as input only a satellite-derived height map. From this single input, our system is able to generate a complete 3D city model with geometry that is consistent and detailed, and with appearance that is realistic and coherent. This is important because existing methods often rely on multiple auxiliary inputs, such as segmentation maps or multi-view images, and are typically restricted to 2D rendering, which results in severe artifacts in the generated cities. In contrast, Sat to City produces an explicit 3D representation, which makes it scalable and much more practical for real applications. Now I'll give you a high-level picture of how Sat to City turns a single height map into a full 3D city, from a conditional point cloud to geometry and finally to appearance. From the input height map, we elevate it into a conditional point cloud. This provides a 3D cue that conditions our first diffusion stage. We start with a dense geometry latent that is conditioned on the encoded height field point cloud. After denoising, we decode this latent to produce an initial explicit structure, a sparse grid with geometry and per-vertex normals. Think of this as establishing the global spatial layout and a clean structural scaffold informed by the height map. We further condense the geometry structure with a sparse geometry latent. And finally, we denoise appearance on decoded sparse geometry, resulting 3D consistent city generation. Our implementation AdoptX-Cube's sparse voxel grid as a unified neural representation for joint geometry and appearance encoding. We start from the input height map, which is lifted into a sparse conditional point cloud. This point cloud provides the initial geometric cue for our model. From here, our pipeline is built upon 3 cascaded stages. The key motivation is that a single-stage diffusion process is not sufficient for large 3D city scenes, especially when we also want consistent appearance. We, firstly, generate a dense and sparse geometry latent grid following the X-cube paradigm. This stage progressively refines the geometry and records upsampling, pruning decisions of latent grids. So when it moved to appearance generation, the latent grid structure and its multi-level pruning decisions are available so that the network can focus on color learning. One important design in our pipeline is the rehash operation, which happens at the VAE bottleneck. Sparse voxel grids are very good at representing geometry efficiently, but they are not ideal for encoding smooth textures or global color context. If we just assign color to sparse voxels, the optimization quickly becomes noisy and inconsistent. So, at the bottleneck, instead of keeping only one resolution of sparse voxels, we progressively coarsen them into a hierarchy of grids and assigning them interpolated values from neighboring vertices of the finer level grid. Each level doubles the voxel size and provides a smoother, more global view of the appearance field. These multi-level feature grids allow the model to interpolate appearance more stably. Each coarser voxel inherits interpolated features from its neighboring finer-level vertices, ensuring smooth transitions across scales. In the first stage of appearance, VAE training, we focus purely on geometry. The sparse VAE is trained to reconstruct geometry and surface normals from the voxelized point cloud. At this stage, the appearance branch is disabled. The goal here is to obtain a stable and accurate, sparse, latent representation of the city's structure. In the second stage, we bring in appearance. Now, the sparse latent from stage 1 is reused as the finest level appearance grid. On top of this, the rehash operation generates progressively coarsened grids. These multi-level appearance grids are then decoded together to predict vertex colors. By training appearance after geometry is stabilized, the model can use the already learned structure as guidance, while the rehash hierarchy provides multi-scale context to make texture learning smooth and consistent. Another important part of our pipeline is inverse sampling, which we use for appearance learning. Our training is conducted on sparse voxels built around colorized point cloud. We explain the inverse sampling strategy by assuming a voxel contains 2 points with different colors. Rather than directly assigning each voxel a raw color from the input point cloud, which could cause significant color conflicts, we allow the voxel to learn its vertex color by predicting the color of points within it. This way, the model is implicitly supervised. The predicted colors must reproduce the point cloud colors when sampled back. This design has two big benefits. Firstly, it avoids noisy or conflicting color assignments at the voxel level. Secondly, it ensures smooth and consistent appearance transitions across neighboring voxels. On the left is City Dreamer. It needs both segmentation and height maps, and it only produces 2D renderings that must be reconstructed into meshes. This often leads to distorted geometry and messy textures. On the right is SAT2 City. We rely only on a height map and directly generate explicit 3D geometry with consistent appearance. As you can see, the buildings are clearer, more regular, and the textures are stable at city scale. Thank you for your attention. For more details, visual results, and updates, please visit our project page.